Good afternoon. So today we will finally see some real telescopes. Optical telescopes, radio telescopes, X-ray telescopes. But we need to do some work to understand how they really work. And so we start with a general introduction to optics. This is very basic. In fact, yesterday I was walking around here and was looking through the window, and in one of the classrooms next door, there was someone explaining exactly part of it. So I'm sure that some of you must know about this. Okay, but before we get there, actually, I have some homework from last time. Ignacio mentioned the fast Fourier transform, and I realized it would take too much time to actually explain what it really means. But maybe it's good if you have heard the term before, because the fast Fourier transform is very popular for many computations. In fact, most people who do Fourier transform use this fast Fourier transform. And the main difference to regular Fourier transform is that it's, well, the main reason why people use it is that it's fast. And it goes back to, there are many algorithms now around, and it goes back to that one. There is no slide on that, no in the handouts. And I will not ask you about that either. This is just now for your information. The main point is that for the fast Fourier transform, the algorithm here breaks down a regular discrete Fourier transform into essentially some sort of product of two smaller quantities. And because it's smaller, the Fourier transforms on these parts works faster, and so you save. And the way to save in computation time is that for any Fourier transform of n points, you don't need to do 2 times n squared calculation, but n times the natural logarithm of n. And just to put this into a number, so let's say you have 1024 points that constitute your data series. You do a Fourier transform, a regular one, you have more than 2 million computations on your computer. And if you do this fast Fourier transform, you only have to do about 50,000. And
let's point out that if you do that in 2 dimensions, the gain is just huge.
Absolutely. And yeah, let's just say most of it do it on images in 2 dimensions. So the difference is not just the convenience, the difference maybe between doable and not feasible. And so there are some limitations, so that's why we can use it. The other thing we did not finish yesterday on Tuesday was that part. And that's an important, it's interesting or important in 2 regards. One is that if you want to build an instrument, you need to ask for a lot of money to build it, and then you have to tell the people who give you the money what the instrument will be able to do. Right? You can't just say, oh, I'll do something, and then I'll see what it does. You have to estimate what will be the performance. What will you be able to see, and what kind of sources will you be able to detect. The other thing is that if you want to use this instrument as an observer, and of course now that's much more important for you, as an observer, you want to know if you can achieve in your observation what you want to do. Right? Let's say you write a proposal for the Hubble Space Telescope or for some DLT or telescope elsewhere. You need to estimate how long you need to integrate. Right? You can't just ask for 3 nights and say, oh, it's probably enough. The time is very valuable. So you have to justify why you need the time, and so you have to make some estimates. And so that means that you or someone else has to calculate the signal to noise, and that's of course obviously the ratio of the detected signal, which includes its own noise, like the photon shock noise, divided by the noise from all kinds of other sources. And there is some pixelation noise, there is some background noise. The background noise, when we talk about detectors tomorrow, we'll learn about read noise, the noise from the dark current, but there is also noise from the background, the thermal background, the fluorescent background of the atmosphere, for example. And all these sources again have some components. They depend obviously on the intensity, which is depending on the wavelengths, on the size of your field of view of a single pixel, for example. You can put that all together and then you end up usually with equations like that, which have a couple of these components in there. They're always incomplete, but it gets very complex very quickly, and because of that, many observatories don't require you to do it all yourself, but offer you some webtool. So this is just something I got from this is how the website looks like. This is a so-called ETC, which stands for Exposure Time Calculator, meaning it will calculate for you how long you have to expose in order to get a certain signal to noise. So, okay, you can here, for example, you can say, well, you have to, if you want to detect a black hole. Okay, you look, sorry, the star. You assume at first order it's a black body, so it's different if you have a certain sort of a maser or some line emission, some line from a quasar, and or you can provide your own template spectrum, and then add certain conditions like air mass here, or the scene at the time of. Sometimes for remote observing, you can specify what the minimum quality is that you require. So obviously, if you have a better scene, that means that your star is not spread over a large area. The light is more concentrated, and because it's more concentrated with respect to the background, you also will get a better signal to noise. But then you have to justify it, because obviously everyone wants to get a good scene, and the telescope has to be operating all the time. Okay, and this is so this is the form, and then you somewhere you press enter, and then it will tell you in order to reach a certain number for the signal to noise.
I don't see the data there.
No, this is the website. I mean, the HTML page, of course, goes to the second floor, the first floor, and so yeah. I just wanted to give you some feeling of how these websites typically look like. And yeah, I like to leave it at that, and then start with okay, let me ask you again, just as a consistency check. Who has a telescope at home? I know we use it in Bogota. And okay. So we have 3 telescopes. Who has ever been at a telescope? I mean, visiting some observatory. Okay. So, optical telescopes? Okay, very good.
And the space is
Who has been to the outer space? Yeah. Okay, so let's start with some basic geometric properties. Now, this is really just that you have a record or you have a reference for the terms, for the terminology that I use. Let's just use the simplest imaging system, which is a pinhole camera. You can easily build it yourself, right? You just need a dark box and put a screen in front, drill a hole in there, and you get a pinhole camera, which is very simple. If you describe it simply by geometric optics, right? You trace the ray essentially from that point, and it will land on the screen here, from here, so you can easily see that the image will be upside down. Okay. Now, of course, the pinhole camera is not ideal. It's not a perfect system, simply because, I mean, the hole has to be a finite size. If you make it too big, it will not work for the reasons we see in a minute. If you make it too small, well, there will be no light entering the camera, and you won't see anything. Right, so let's say from one point you always have, you have the size of a certain hole, you have an angle. The beam coming from that point here, of course, that's a certain angle. And that will be imaged here. Same here, but you can see there is no real focusing. Right? If you put that screen further away, or if you make the hole bigger, then this beam also becomes bigger and the whole thing becomes very fuzzy. So, problem, of course, is pinhole cameras don't focus. But of course, we could put a lens our focus. Now, okay, this is the, I think, the most basic setup of an imaging system. Let's say here's your tree again, your object size. And just like before we had from this point here, from the tree top, we had a bundle of rays, the beam essentially going this way. And here this would be our pupil then. It would be like a telescope pupil, right? No light outside the telescope will reach our detector. And here for the pinhole camera it's the same. This is the pupil because this limits the beam. And no light outside of this hole will enter the camera. So we have the same here. So the green rays essentially, they define the bundle of rays from any object point. I mean, you can draw the same first from this object point or from this object point. But the size, the divergence of this beam, so the angle here, is simply determined by the size that your pupil, your telescope, or your lens, whatever is limiting the beam, whatever it will accept. Obviously, if you make this what's called the aperture stop, if you make it bigger, then more rays would come in through. Right? You would imagine a ray going up further here will also come through if the aperture stop very large. Okay, so we have a collimator here that just makes in this case, ideally we have a collimated beam, so meaning that the rays here are parallel. Then we have the aperture stop, which is in the system for our telescopes. Of course, this would be then the aperture of our telescope, pupil. And then we have a camera lens here, and the camera lens focuses this parallel beam on one point, and of course it does so for many, many points along the object, and this will produce our image. Okay? So I'm not sure if I have to go about, forget about marginal rays and chief rays. If you don't want to become an optical designer, that's just for further reading. But the main points are here: object, collimated lens, aperture stop or focal stop, camera lens, and you have your image. Okay, so this is the really basic setup. In many cameras or other systems work that way. Sometimes you have them, multiple of them in a series for other reasons. But there is also one additional aspect I should add, a term that's called the speed of an optical system. And as you can imagine, this lens here has a certain focal length. Right? Length at which you have parallel light coming in here. The focal length is the length distance essentially from the center of the thin lens to the focal length. Right? So in this case, the focal length would be roughly from here to here. You could also imagine that we make this lens more curved. So the lens has more power, and then what would it do? It makes the focal length shorter. Okay. And essentially, okay, if you make it shorter, then the rays, the angles here, would also be steeper, right? And then you would what's called have a faster. Now this is important also when people talk about telescope mirrors, because, well, you can imagine. I'll tell you why I'm mentioning this. Maybe the motivation. If you build a large telescope, and here is your telescope mirror. Let's say, let's use this example of a 39-meter extremely large telescope that people are thinking about. Yeah, if this is 39 meters, and you have a very slow beam, meaning the curvature is slow, and this angle here is very small, then the mirror here is almost flat. That's easy to build, right? You don't need to polish very long to get a very small curvature. The problem is, of course, that your focal point is up here. Yeah. Now, not quite to scale, but if this is 39 meters, this is 100 meters. Yeah, so you can imagine that you need a structure inside your observatory, and those who have seen a telescope before, an optical may appreciate this. You have a huge thing. Yeah? You have that's larger than the pyramids in Gizeh or the whatever, the Eiffel Tower you would need in order to have your secondary mirror there. So you want instead the solution, of course, is that you need a very curved mirror, because then your focal point is here, and you can put the whole thing in a smaller building. But that requires fast optics, and you can imagine that building a very curved mirror is more challenging than building a flat mirror. The same is true for cameras. You know there is thermal emission as a background from the atmosphere. Simply because the atmosphere, you know, radiates, so you have background from the atmosphere. But you would also have background from the instrument itself. I mean, what we said before about the black body radiation of the atmosphere is also true for the instrument itself. I mean, no mirror is 100% reflective. It may have some dust specks on the mirror, and of course, if you go to infrared wavelengths, that dust will radiate. So your instrument will add background. And the detectors do not work with room temperatures either, as we will see tomorrow. So you cool down the whole instrument. Just put a big tank around the instrument and cool it to minus 200 degrees or so. So fine, but of course in order to cool something down in a cryostat, you want it to be small. Right? You don't want to have something really huge and put it into a big pure cryostat. And that requires, of course, that you make the optics more curved, that you require fast optics, where this angle here is relatively large, with respect to the focal length is relatively short. So you have a relatively large, what's called the F number, which is the ratio between the focal length and the diameter of the beam. Okay, so this is good to make it compact and small, but if you do that, then it's also very, very hard to manufacture. So every optical designer or instrument builder has to find the right compromise between the size of the instrument, the performance, and how you can actually align them. If this is if this is a very large angle, then of course the alignment becomes very, very tricky. And we'll see this in a minute when we talk about economics. Okay? So this is just another representation of the same thing. I've just taken twice the same optics here, and then I just changed the curvature of the camera lens. And so, okay, here the focal distance is like that, and we get an image that is not large. Now we have a lens with a stronger curvature, and this is the same length here, just for reference. You can see that the image gets closer to the lens. But also, because the rays are more bent here, or refracted, the image becomes smaller. So with that, you also have a control over the magnification of your system. And the magnification, that's simple, it's simply the ratio between the image height to the object height. Okay, and if it gets smaller or larger, this is also one way how you can control the image scale. The image scale being, so the functions of this angle here is simply the ratio between the unit size of the image divided by the focal length. And now, of course, okay, now we know from last lecture about the Nyquist sample. Right? Let's say we look here not at an extended object like before at the tree, but now we look at the star. We would see the same thing. It would produce an image here. Of course, the image is not a perfect point, and we know from last lecture that the size of the image of the point present, according to the Nyquist theorem, should be about 2 sampling elements. Well, we sample with our detector, our CCD. So the size, full width half max of the PSF should be about 2 pixels. And now, of course, we can easily control that, because in this case, we would just change the curvature of the lens. We change the image scale, and we make sure that the image of a star covers 2 pixels of the detector. Okay? I'll skip the last point here. But of course, this is essentially all I wanted to say about geometric optics. But when you go observing, you often realize that you suffer from some aberrations. Aberrations are just departures from the performance of an ideal optical system. It's called prediction of paraxial optics. Like you would just look along the optical axis and everything would follow a simple geometric optic. Generally there are two categories of aberrations. There are on-axis aberrations. And I just listed them here all, the most important ones. Like defocus, spherical aberrations. Those on-axis aberrations, they also exist off-axis, but they also exist, obviously, on-axis. And there are in addition, there are off-axis aberrations. And they usually get bigger when the image size gets larger. Those are coma, astigmatism, distortion, field curvature. And they increase with image size and with pupil size. So that's it. So some of you have glasses. So if you're suffering from coma or astigmatism, then if you go out at night, is your vision getting better or worse? Sorry?
Usually the light is strong.
But I mean, let's say you look at some traffic light in some distance, 200 meters away, during daytime and during nighttime. When do you have the better vision? During the day. And simply because during the day, well, the pupil of your eye, well, I mean, there may be other things.
Because you think in terms of the signal or noise ratio, it's better at night.
Yes, I'm only worrying about aberrations and how blurred the image looks like. But the point is, I mean, I'm assuming if the stoplight is faint, then you have other problems. So let's say you have a bright stoplight that you can easily see. Then at night, of course, the pupil of your eye will grow in size. It will get bigger. And if the size of the pupil gets bigger, you also get stronger aberrations. So that's, I think, when you suffer from astigmatism or coma, and you go observing just with your bare eyes, then you have a particular problem. Okay. I should add one slide here. I put it again in parentheses because this is just for maybe for clarification, because I'm mixing here throughout the whole lectures, I'm mixing two things. Sometimes I say, okay, there is a plane wavefront coming into the atmosphere. Yeah, so we have the wavefront, and then there is the atmosphere, and that means that the wavefront is distorted. But I'm also using a separate picture where I say, okay, for the pinhole camera, I have the light from a point traveling along a ray, right? So I'm using actually two different concepts here: wavefronts and rays. And this is simply to show you that it's the same. It's just a different way of doing it. Let's assume you have a perfect wavefront at close to infinity, so it's almost flat, slightly curved. Maybe this is the dashed line here. Let's look at this green S. And if we had a ray coming from here and from here, they would all be focused to the same point here. Okay? But now we distort the wavefront. So we have this is the solid line, it has just some distorted shape. And so the nominal location of that point that would correspond to Q is now a little back here. Also, of course, different tilt here. So it means that the ray is going in a different direction, and we would have an offset here. So, and of course, so then the distortion of the wavefront here means a blurring of the image here. So this is just to illustrate that while I'm mixing here wavefronts and rays, it's really equivalent, and you can transform one into the other. Okay, this is just because I know sometimes people are worried, are confused that I'm mixing things. Okay, let's talk about aberrations. The simplest or the aberration that you suffer most easily from is defocus. If you have ever observed at the telescope in the old days, you could actually control the focus of the telescope, because when the temperature changes, for example, at the observatory, then of course the telescope is a big structure, so the support for the mirrors is thermally contracting, and the focus may change. And then you have a panel, it's like a whatever you control for the Xbox, and then you could adjust the focus. And defocus simply means that your focal plane is not where it's supposed to be. And you can see, of course, obviously in this picture, this is where the image is focused, and this is, let's say you accidentally put your detector here. Right, then obviously here, the point that would be here, the point is here spread out over a much larger area, meaning your image is fuzzy, if you're not focused. And you can see here also why people don't like fast optics, as we said before. If you have a lens that gives you a lens with strong curvature, right, so here would be your nominal focal plane. Now unfortunately, if you put your detector here, right, you have very fuzzy images. Okay, but if you of course have a very slow optics, okay, here's your detector. Let's say you misplace it by the same amount. It doesn't matter much. Right? And this is a problem for optical alignment. This is actually a problem if you have a smartphone. Yeah? Who has a smartphone? So take pictures. Yeah, but the thickness of your smartphone is just whatever, half a centimeter. So all the optics, there are lenses in there, of course. They have to focus the image onto some CCD chip in your smartphone there. And you can imagine that that lens can't be that, right? Your smartphone would not fit in your pocket. So it has to be very fast optics. So the alignment of those devices is extremely critical. And yeah. And you can actually characterize that by a term called the depth of focus. It tells you essentially how accurately, and this NA is the numerical aperture or the F ratio that we defined on the previous slide. So this depth of focus tells you essentially what the tolerance is within which you have to put your detector. Okay? So defocus is I mean, again, this is the aberration that you can sort of fix by moving around the focal plane.
This, this NA,
Yes.
it's called numerical aperture, yes. It's okay, it's
Here.
some kind, depending on the focal length. Of course, it's depending on the F number.
Yes.
So a large F number means a small NA, okay?
I have to always think about it. A large F number means that you have a large F okay, and then you have a small F.
So it's harder to focus. It's harder to focus the telescope with a small delta, right?
Yes.
But this delta means that it's harder to focus a small delta telescope. So a small NA telescope.
Yeah.
If your telescope has a small focal length, it will be harder to focus on.
Telescope has a small focal length is hard to focus. Yes.
Or you can also say that it will be a larger tolerance, the focusing. Meaning
Smaller tolerance.
smaller tolerance.
Well, if it's larger, the tolerance is smaller. Right? You have less room to play around.
Okay. Okay.
Okay? Now, of course, I mean, you would say it's stupid, why don't I put the detector in the right focus? But we're really talking about fractions of millimeters here. So it's really hard to get the right focus. Or if we talk about 50 micrometers or so sometimes to focus that.
And what about infrared versus optical telescope? It's harder to focus an infrared telescope. So
Everything gets easier at long wavelengths.
so
No, sorry, I take that back. Optical, right? Not everything. Optical. In that sense, in terms of alignment. Because all the aberrations, what you can accept and so on, it's always with respect to the wavelengths. Okay, so yeah, I mean the wavelength here is shown here. Right? So your depth of focus increases linearly with the wavelength. Okay, the next aberration is spherical aberration. Because it's interesting. This is a gray shaded lens which is completely disappearing from here.
but it's there. It's in the screen.
Can you see it in the handouts? No. Okay, okay, it doesn't actually matter. Just imagine there is a convex lens here. Yeah. I think maybe I should just redraw it here. So the problem is for a lens, you have parallel light coming in. You have the rays focused here. Right, so the lens is supposed to be here. But the focal point here, and we'll get back to that when we talk about telescope optics, is different from the focus of lights, of rays that are closer to the optical axis. But you always have you have the full lens illuminated, right? So you have sort of a range of optical distances. There is no way to put your detector at the optimal distance, because the optimal distance depends on the size of the lens or of the telescope. And that's, yeah. That is a problem for all spherical optics, and we know there is a solution to that in S-sphere, but we'll get to that later. The most famous example maybe of spherical aberration is the Hubble Space Telescope. And so when people launched the Hubble Space Telescope, everything looked to be fine. And it's been tested many, many times, and it had superb image quality. And they looked at the first star, and the first star looked like that. So the first galaxy looked like that. So this was an image that was taken after the refurbishing mission, right? After they sent up an astronaut to exchange the camera that correctly for that spherical aberration. But I mean, there would be no one would be so proud of the Hubble Space Telescope today if this were all that we would have. And actually, the problem is that in order to test, this is a short excursion now, but in order to test this, the primary mirror of the telescope, which is not a spherical mirror, in order to exactly avoid that, you can easily test spherical optics, like this lens here, but with an aspherical mirror, it's difficult to do it in the lab if you have only small distances. With small, I mean less than 20 meters or so. And so they had to correct the lens there to make the testing of the mirror simpler. And that setup of the correcting lens, that was misplaced by 1.3 millimeters, I believe. And no one has tested carefully the test setup. So it was a perfect mirror according to a incorrect test setup. Yeah. So this is, yeah, okay, and because you test it again and again and you get always the same result, you're convinced everything is fine, but you don't test the test setup. So
it's like having the heat confirmed, but with a bad thermometer saying that it's good. So it's something, oh, very good.
yeah, okay, so now of course, the good thing about this was that because they had, of course, the test setup still sitting in the lab, of course it was not launched, they could just measure that after it was launched, the test setup, and figure out exactly what was going wrong here, and then build a corrector for the incorrect Hubble optics that was then automatically put in the next instruments. So all the instruments that were then placed on the Hubble Space Telescope had this correction done, and they know exactly what they needed to do because they had the incorrect setup still sitting around at NASA on the ground. Okay, and
the Hubble Space Telescope is the best imperfect telescope in the history of the humanity.
if you like, yes. There are books that have been written about this problem. Seriously, books. And that is, the books are interesting in the sense that they had another test setup that gave the results that showed that this is not right. But the other test setup was cheaper, and so people, it was just nice to believe, well, it's probably not working. We believe the expensive test setup that had the problem. So it was not a problem of optics, it was a problem of management. And this is what the books are all about. Yeah. Anyway. Okay. So there is one more. I could go through a long list of aberrations, but I just want to show you one which is important since we talked about lenses, and that is chromatic aberration. I mean, the reason why a lens works, of course, is that the rays here are refracted, and the angle of refraction here depends on the refractive index of the lens material. I mean, if you take the same shape but a lens with a different material, will give a different refraction of the rays. But for essentially all materials, the refraction here is the amount of refraction is wavelengths dependent. So different wavelengths have a different, the lens has a different refractive index for different wavelengths. And that means that the focus is different for the red light than for the green light or for the blue light. So, and actually I took this image from Wikipedia a couple of years ago, and I now checked and it has to be corrected, because there is something wrong with that figure. Anyone have an idea what's wrong with that figure?
Sure, isn't it the other way around? Like red has a lower end?
Right. So the red light, as we said before, longer wavelengths are almost always less affected by almost everything. Also by refraction. So the blue light is actually the one that should be refracted stronger and have the shorter focal length, and the red light should have the longer focal length. So if you check, I think if you check Wikipedia for chromatic aberrations, you'll find it correct. One way to correct for that is to combine two lenses with different materials, and then you can take out this effect to some extent. So in one case you have a very strong, what's called that, dispersion. In the other case you have less, and if you then tweak the curvature, where you can control the focal length, and the combination of the materials, you can construct what's called an achromatic doublet. And that's you find, so in many cameras, when you look at the optics, you often find doublets, essentially always pairs of lenses. And that's essentially for the reason shown here, that you want to get rid of the chromatic doublet. Okay? So if you want to know more about aberrations, this is the slide for you. And again, I think it's going too far, so that's why I put it in parentheses again. If you know if it's there, I don't ask you for details in the next exam about this. But it's just listing how, let's assume you represent a star by a number of rays, each of which gives a point in the focal length. So that's a typical, I mean, that may be literally a point disparity function, because it shows you how the points are spread for a PSF. And if you have, just let's look for one axis, so you can easily see that coma, astigmatism, view curvature don't exist on the axis. If you put your detector on the axis of the optical system, it doesn't matter. But if you go off the field, so you look at a galaxy or so that has some large extent, so you want to make sure that the off-axis points in the corner of your field also look nice, then you have a problem there. Because if you have coma, all your points here have this tail here. So it really looks like an extension to one side. And for astigmatism, well, these are all extended. And then it depends on whether if you go slightly out of focus, sometimes the shape becomes extended. And when you do an optical design, you have to optimize all the curvatures, all the materials of the lenses to make all these blobs as small as possible. And the problem is there are some scaling laws, so this is not always possible. Like here, for example, the, let's say, coma depends on the third order of the pupil size. Meaning, that goes back to my you watch the stoplight at night example. So if you're at night, you're idled up at depths, and the pupil gets twice as big. Then you have 2 to the third power, so the coma will be 8 times larger than what you would have during daytime.
The other way. Oh, please repeat.
At night, you would have times as much from coma than during the daytime.
No, the other way around.
Because your pupil size increases.
Yes.
So yeah, and there is also a dependency on the image size. So if you have a big field of view, now the astigmatism, for example, increases to the square of the image size, which for many systems gives you a limit on the performance of your telescope. Or, I mean, ideally you would like to have one gigantic detector there and or a photographic plate or whatever to image the whole sky at once. But because the aberrations increase with the square of the image size, there is a limitation to what your optical system can do. There is no way in a single exposure that you get very sharp images out to a very large distance. And of course, if you have a scene-limited image, usually it's not noticeable. But if you have a diffraction-limited image, like the Hubble Space Telescope, you see with adaptive optics, maybe if you go to very large image sizes, then the quality of the image is limited by the aberrations. And so you have a natural optical limitation on how large your field of view can be. And that's a big constraint on, say, all sky surveys. So you often have to piece it together in small places.
From another point, how is modified the PS function when taking account these operations? I mean, the PS
Yeah, I'm sure your point is
modified.
right. And it's essentially a convolution. So you have the ideal PSF, so the one we calculated last time, right? With the Bessel function in there. So you have this ideal PSF that's given by the size of the pupil. And then after the telescope, you have, say, your camera optics. And that produces additional aberrations. And the resulting PSF that you detect is the convolution of the, so not the simple mathematical product, but really the convolution that we can calculate now, knowing about Fourier transforms. The convolution of the telescope PSF is aberrations. Meaning that if you have an astigmatism or a coma here, and a fairly nice PSF, then essentially all the points, all the PSF would have the structure on top of the nice PSF. Okay, now that you mentioned it, let me come back to the pupil diffraction and the PSF. So this is maybe not new, but it doesn't help to repeat what we discussed last time, maybe in a slightly different.
I have a question. Why? I know that Hubble telescope takes its images the focus in order to measure, to do better photometry. What is that? Why do you have to be focused to get better photometry?
Essentially, you oversample, and so you measure with many more pixels. And so you depend less on flat fielding, and you don't need a real image. You just, I mean, your stars are point sources. There is no information to gain if you have sharper images. And since they're bright, you don't have to worry about the loss in sensitivity when you oversample. And yeah. I mean, oversampling with many pixels it's like if something happened there, you go out on the street and you ask one person what happened, you'll get an answer. But I'm not sure, maybe this is a strange person, or maybe he told you some whatever story. So you ask more people. Yeah? The more people you ask at first, the more certain your average gets. And if you look at very small fluctuations on calculating your light curve, it's good to have many witnesses, many detector pixels, so you defocus. Okay, let's say, again, this is your star at very large distance, almost infinity, and you have a a lens here. Telescope, yeah, again, you may say, I've seen this many times before now, and you're right. And the size of the telescope or the lens or whatever that is the pupil of our imaging system determines the size of the cone of light that is accepted of this object. And then we call again the light again, the light again, and not call it, sorry, we focus the light, and the image here is determined, or the point spread function that we see is simply determined by the shape and the size of this lens. And we discussed last time, the amplitude of this field here is the Fourier transform of this field function. Okay? So much to remind. In other words, now it gets really simple. If you have a point source at infinity and you have an infinitely large telescope, you get a point. If you had, like in reality, a point at almost infinity, a finite size telescope, then you get this diffraction image. This point spread function, which has a central spike, central peak, surrounded by some diffraction. And this is called actually, I mean, we said last time, we didn't really give it a name as a function. We said this mathematically, this is the function, and you can calculate it in this way, and it depends on the first order Bessel function. But actually, this complicated term has a simple name thing. It's called an Airy function. So if you hear astronomers talk about an Airy function, they're usually referring to the function of that expression. In one dimension, it looks like this. So it has the central peak, and then surrounding it, you see those, it's called the diffraction rings. So obviously, that only works for diffraction-limited optics, meaning there's no atmospheric turbulence or so that degrades your image. In two dimensions, it would look like that. You have the peak here, and then you have these wings around these rings. Okay, and the radius of this first ring, the dark ring. So if you go to the center here, and you measure the distance between the center and the next minimum, which is this figure here, so that somewhere the minimum here, dark ring means no intensity, right? So the distance between here and here is given by the simple formula here. Alpha angular space is 1.22 times the wavelength divided by d, where d is the size of the pupil. Okay? The diameter of the telescope. And often people refer to the full width Fmax, and that was the question last time. So you can characterize the width of this PSF since it scales diameter, but since everything scales, you can simply characterize it by the size of the full width Fmax of the central peak here. Yeah? Full FWHM means full width Fmax, and so you can measure it. And the full width Fmax, that's the part for an optical system that you would like to have critically sampled for maybe overscan. So you would have to, in this case, where you would have now to put a detector here, you would like to make sure that this part from here to here is covered by at least 2 pixels. Okay? So this is an important equation here, because this tells you about the resolution of your system. Of course, as we said last time, I could have put it also in parentheses, but so the numbers are not so important, it's more what's happening qualitatively. If you add an obscuration to a telescope, of course you have a modification to your, what we call the box function yesterday, or on Tuesday. And then you had a more, well, maybe a donut function, I don't know. And then you can also use the same formalism because it gets a bit more complicated, and you have to add another term that contains this Bessel function with a factor here. And that factor here is the fraction of the central obscuration to the total pupil area. In other words, if you have an 8-meter telescope and you put a secondary mirror above it that's 1 meter in diameter, right? Obviously that fraction is 1/8, so epsilon would be whatever 0.125.
You said area, is that the ratio of the radius or the ratio of the areas?
That's
You said 1/8.
yes, I think it's
And that would be 1/64. Is that still like the area or like the radius?
now you got me here. I have to check.
I think it's like the radius. Sounds to me like the radius.
The rate.
I may be wrong.
Yeah. I'll tell you tomorrow. Because this,
This E squared could be line. E squared could be that it is radius instead of area, right? Okay.
By the formula, it looks like the radius, not the area.
it looks like the radius because you
Looks
square
like
the
the
radius
radius,
anyway,
yes.
right? So it's the word that's wrong.
Yeah.
Okay, but I mean, again, remember what we said for the simple case of a continuous pupil, your first start rank would be at 1.22 lambda over d. And now you add some central obscuration, and now it's not at 1.22, but it's actually getting smaller. So if you have half of the telescope size covered with the central obscuration, then actually you would be able to have to make your central peak, the central peak of the star, your PSF, smaller. Appear smaller. Right? So this is the point you should take away from this is that the central obscuration matters. It determines how your image looks like. The rest you can forget, but remember that it's all changing when you add something to your image.
But it looks like it's getting better, but actually it's getting worse because the secondary rays are getting higher. So actually it looks better.
It depends, of course, what you want to do with the secondary rays. I mean, if you say
The
you want
secondary rays
to
will increase. So
yes, but if you want to observe a double star,
okay.
let's say Archer wants to see his planet next to the star. He doesn't care about the secondary ray, because his planet will be as close to very close to the star, and then what matters is only this number. Right? So in principle, a telescope with a large central obscuration would help you to detect that. Only that if you make it too large, you have no light left. Okay, and then this is something we already talked about last time in the Fourier transforms, but I just want to remind you that the story, of course, is more complex. This is the ideal PSF, ideal area pattern of a circular continuous pupil. And if you add telescope spirals, segmentation, maybe aberration, this is what the PSF of Nichols looks like.
What is the secondary node on the top?
I think it's actually a small reflection. I'm not in this case, but I'm not.
It has to be without the node.
I'm just trying to remember if I got that from home data. In which case it might be another star. So since this is recorded, before I claim that there's a reflection in the Nichols optics, let's say this is another star. Okay, and if you have a circular pupil, you get a beautiful PSF. If you have a segmented pupil, you get this structure. If you have many segmented mirrors and spiders, and you get very nasty features there. And of course, at high signal to noise, you will see some of these features. And then it's very tricky to distinguish what is diffraction from the telescope and what are other sources in the field. Here's another example. This is actually data I took with the Hubble Space Telescope with Nichols. So you can see for every star here, you can easily see, this is at 2 microns, this is a dense star cluster in the Large Magellanic Cloud, you can easily see the area rings, at least the first ring. You can see, I mean, here's the peak, here's the dark ring. Right? Now we know the distance between here and here in angular space is 1.22 times wavelengths over telescope diameter. I mean, you can even count the pixels and prove if I'm right or wrong. And but then you can also see the problems that there are if you have many of those. Because sometimes the rings around the bright stars are brighter than the peaks of the faint stars. Okay, so you mix it all up, and analyzing these images is tricky. Okay, so what is the resolution? How do you say this is a short image, this is a not so short? And the first definition that people still use goes back to Lord Rayleigh. It's called the Rayleigh criterion.
Let me ask you something that comes from my experience with amateur telescopes. I have this question about these peaks in the images of the stars comes from these diffraction patterns due to the spike, right? This is the first question. When you see this clear star pattern full of these peaks, these are diffraction in the optics of the telescope. Okay, but it even appears in your eyes when you don't have this spike. So, how do you produce this kind of patterns in open optics?
For the eye, actually, I'm not sure. For any other optics, not everything is perfectly rotationally symmetric. Okay, that's the main thing. I mean, one is the angle in the atmosphere, the transmission through the lenses, and some angle. In many cases, you have some square apertures introduced somewhere. I think one has to look at each individual at the optics, but it's certainly true that this is completely different. So the Rayleigh criterion states, and this is very empirical. It was essentially Lord Rayleigh just was wondering, when can I resolve two double stars? So he was just wondering if he has two sources of equal brightness, and he said 2 point sources are regarded as just resolved when the principal diffraction maximum, so let's say this is one star, the maximum is here, of one image coincides with the first minimum of the other. So for that picture here, the first minimum would be somewhere here. Right? And he says that if the peak here falls on top of that minimum for the diffraction from the other source, then I can still resolve it. So in this case, it's about here. So here's the peak, it goes down, here's the minimum, and here's the peak of the other stars. So the light profile would be something like that. If I would look from the top, right, if I would look at what my detector sees, I would see that there is it's like a double star. The one that almost looks like the system we talked about before here, right? You see the rings around the planetary system maybe, and then you have another binary here. Well, but the point, of course, is that you will be able, because of the peak here, the double peak structure, to still resolve the sources. If they get closer together, there is no way anymore to tell that these were two sources. If they're further away, then it's easy to distinguish them. So the conclusion is the minimum resolvable structures are given by this equation. So either sine theta is 1.22 lambda over p over d, or in radians, then the physical distance at the detector. I mean, this is of course an angular unit, right? 1.22 lambda over d. This is the angular space on the sky. But of course, you can also say what would it be millimeters, and then Okay, just to show you what does this actually mean, the angular resolution. So essentially, how large is 1.22 lambda over d for some examples. Now, for the human eye, well, the resolution is about 1.7 arcmeters, but that's not just given by that resolution. But for a 6 centimeter backyard telescope, it's all at let's say at 500 nanometers, so visible wavelengths. With your 6 centimeter backyard telescope, you would be in principle able to resolve 2.1 arc seconds on the sky. So 2 stars that are about 2 arc seconds apart, you should be able to see, if there were no sea. If you go to the 3.5 meter long inversion telescope, which is located on the Homa, 3.5 meter mirror, then the resolution, if you compare it here, I mean, it scales essentially just with 1 over d. So you have just a ratio of 3.5 meter over 2 centimeter gives you the difference between 2.1 arc seconds and 4.04 arc seconds. If you use the 10 meter Keck telescope, of course, it would be another factor of 3 better. But let's say if we use the longer wavelengths, since it's 1.22 lambda over d, since the wavelength now is 4 times longer, also the telescope is 3 times bigger, the wavelength is 4 times longer, the resulting resolution is slightly worse. And of course, the problem of the wavelengths is an important one, because if you then have a radio telescope, 25 meters, you think it's a big telescope, right? 25 meters, but because your wavelength is very long, say you have radio wavelengths of 10 centimeters, your resolution is only 16 arc minutes, worse than one of the human eye. And that's the reason why, of course, people like to combine radio telescopes over large distances to get then with an interferometer, which we're going to discuss next week, you'll get then resolutions that are comparable, well, at least with your backyard telescope. How large is your backyard telescope, Rafael?
6 centimeters.
Okay, so again, remember, this applies only to diffraction limited systems, so we did not include seeing here. And if you don't know what an arc second means, take a hair. You can pull out one of your hairs and at the right distance and hold it. So then the angle, or the angular diameter, the size I will see your hair, 10 meters distance, that would be about 1 arc second. So it's really a tiny angle.
There is an interesting contradiction here that has to be pointed out. And when you look at the telescope from the point of view of the wavefronts, the larger telescope should be worse than a smaller telescope. However, in spite of what you said here, that it's only diffraction limited, the experience has been even taking account the sea, larger telescopes can resolve much better than smaller telescopes. Why?
Because if you remember the first lecture on the turbulence, we knew that the C, or the resolution, or the size of the source, was of course then not lambda over d, but lambda over r naught. R naught is the free parameter. That's the size over which we consider the wavefront, the atmosphere flat or non-turbulent. And we said that this size scales with lambda to the 6/5 power. So for longer wavelengths, the sizes are large. And it's not even linear, it goes to the 6/5 power. So if you go to wavelengths of not 500 nanometers, but say 5 centimeters, then what's the vector in there? Okay, I'm getting tired, maybe you can tell me exactly. Okay, 500 nanometers, then we have 5 micrometers would be a factor of 10, 5 centimeters, that would be then 5 millimeters would be a factor of 10,000. So we have a factor of 100,000 wavelengths. So then the size over which the turbulent atmosphere can be considered non-turbulent is huge, much larger than your telescope. And so it doesn't matter. So that's why usually long work with the existing telescope on the ground, if you have wavelengths longer than 10 micrometers, mid-infrared wavelengths, usually you're okay in terms of C. So the turbulence in the atmosphere is usually only a problem for wavelengths shortward of 10 micrometers.
If I recall that they were claiming that they were reaching the fraction limit at K, wavelength K, which is 2 micrometers. I think it was
Well, with image selection. So my statement was average, but as we all know, there are good nights and there are bad nights.
Oh,
and if you wait a year, then you may have indeed a night where you can get to the diffraction limit at 2 microns. But don't count on it. It's very unusual. It's more complicated than that because at radio you have other nasty effects. Because they have something similar happening in the ionosphere. So for long wavelengths, that's the good thing. You're usually diffraction limited. So let me just show you another more qualitative example, because the criticism has always been that the Rayleigh criterion is, well, it's very subjective. That's what Lord Rayleigh thought is right, and it works fine. But a better measure for the evaluation of any optical systems, and that's probably what people around here in the say physics, optical sciences use, is the modulation transfer function. Imagine you have a pattern or a mask. Just put some dark bars on your mask. Just don't look at the bottom one. Right? Just look at the top one here. And it's not different from when you go to the optician and say, I need new glasses, and he gives you maybe something like this and say, well, what can you see? Okay, so you have here a pattern of dark and white and bars. And of course, so the distance gets smaller and smaller, or the intensity would be something like that. And now you add some aberrations to your optical system, meaning that the aberrations just blur the image. Well, the aberrations don't matter really when these features, when the structures are far apart. But somewhere here, of course, you can't see anything anymore. It's just mixed together. And so you have no contrast left. Right? And essentially, this modulation transfer function is a measure of the contrast that you have as a function of the spatial frequency. Right? Remember what we said before, last time? Here you would have the density here of the bars is very high, so you have a high spatial frequency, F. Here you have a low spatial frequency. So this contrast will, it's just normalized here, but this contrast will go down with higher frequencies, whereas here you have still good contrast. Right? While contrast, as we've heard this before, contrast is just defined here as the difference between maximum and minimum divided by the sum of the two. Okay? So the contrast goes down with higher frequencies, and this is, I mean, in this case, if we would plot, if we would make a cut across from left to right, this would be about the function we see. Well, it would not be harmonic, but you would have some shorter edges, but it's qualitatively this is what you see. Whereas if you have some aberrations, then you would see it go down, and you could, for any imaging system, you could always say if the contrast is less than modulation transfer function is decreasing for a certain frequency, that tells you exactly how much aberrations you have and how much detail you can resolve in your image.
What's F? Frequency or?
Sorry? F is the frequency, spatial frequency. Right, in other words, the lines per unit, like 5 lines per centimeter. Right, so, I mean, I can measure it here. If I say, I can define F as, say, 10 centimeters, so I have a spatial frequency here of whatever 8 lines per 10 centimeters, and here I have only 1 line per 10 centimeters, and this is shown here.
So if you think in a number, which is the number, and you think about the modulation function. Because relative to the theory of a number, this is an answer. Here, what is the number?
I wanted to measure it because the rating criterion makes a lot of sense. It's intuitive, and if you have a double star, it's obvious. However, if you have some optics to measure, you do not always have, in the lab, for example, you put some lenses together and you want to see how the imaging system performs. You don't have a double star and you move the stars around and say, okay, now it's good. You use some masks like that. And you look at the mask, you know exactly, I mean, it's really like an optician that shows you whatever a board with numbers on it and says how small of a number it is to read. And this is similar here. So you just look at this pattern, put this in front of your optics, and you look at it at the end, and then you know how much detail you can see.
So if it's perfect at a given frequency, it will give you a 1.
Yes.
And if it's flat, it will give you 10 to the minus 3.
Yeah.
So it's a continuous scale.
It would go down, I mean, the contrast goes down as shown here. Right? And of course, if you know that in angular space, my double stars, or the separation between my star and my planet, is at angular distance that corresponds to a spatial frequency like that, and you use the telescope, this is a bad choice, because this will never be able to resolve what you want to do.
So this tool is also a characteristic property of the optics.
Exactly.
And you see the threshold with the representation of
So, in other words, this is simple and made by astronomers. This is complicated, but is applied by everyone in the optical industry for measuring and testing and so on. So, yeah. And there is a final quantity I'd like to measure here. I may have never heard before. It's named after an optician. It's actually very simple. It's called the Strela ratio, and this is simply the ratio between the peak intensity of what you get if you have perfect optics and the peak intensity that you really get. In other words, let's see, you look, we said before, ideally you have an airy pattern, so you have some expectation of what your image will look like. But then you look at it, and the image looks more like a red curve. Okay? So it's just not as nice. And that is simply because of the aberrations, not all of the photons in there, not all of the waves will interfere according to our Fourier theory. But instead, because of the aberrations, some light will be deflected in some other directions. So you will not have all the light that you would like to have in your central peak, in your central peak of the PSF. You will have somewhere else in your image. So an optical system with aberrations would give you more like that curve, and the result is simply that the peak here is less. And remember that the light, essentially, which is in the central peak, that determines the brightness of your star. Often, whatever happens out here doesn't really matter because it's too faint, spread over too many pixels. So if you have a faint source on the sky, what matters is how much light you do have in the central part here. And this measure can be, a good measure of that is the Strela ratio, because if the Strela ratio is 100%, you know you have excellent imaging performance. And if the Strela ratio is much less, then your sensitivity, your signal to noise will drop, simply because the noise will still be the same in your image, but the signal will be that much less. Okay? So now this is for diffraction limited PSFs again. So if you have, I mean, like for the Hubble Space Telescope. I mean, if you remember the Hubble Space Telescope image, okay? So maybe I should actually go back. It's a good example. Here. Here. I mean, you see all the structures. This is around it. Of course, this is all light. And where does the light come from? It comes from the center. Ideally, you would have a bright peak here and some rings around, but not all this crap here. So the light that you see here is, of course, missing in the center. So that PSF naturally has a very low strain ratio. And that also means that you have a low sensitivity. Because you have a fainter peak. And you can actually calculate what the strain ratio is, but we shouldn't worry about this part. Generally, if the strain ratio is larger than 80%, then people say it's diffraction limited. Just as a number, if you go observing, with the adaptive optics system on the Keck telescope or on the VLT, you typically get strain ratios more in the order of 50%. Meaning that, well, it would be better. You get only half of the light possible, ideally in the central part. You get only half the light if you have, and maybe that's an interesting comparison. If you're comparing to scene limited imaging from large telescopes, you can always compare things. Okay, let's say this would be our ideal okay, this is our area PSF, our area function. So this defines the maximum, and this would be the 100% strain. If we have an adaptive optics system that's not perfect, or we have some aberrations, like we had in the Hubble Space Telescope, well, unfortunately, we will not have all the light in there, so what will happen is we have eventually more light up here, less light here. So in this case, let's say we have 50% strain with, let's say, with adaptive optics. And again, we'll talk about adaptive optics next time. So here we have 100% strain ratio ideal. This is what we really get due to aberrations or something else. Now, if we would turn off the, this is for a large telescope, if we would turn off the adaptive optics system altogether, meaning that we would get only scene limited performance, and we know the PSF would grow, we would probably get something like that. I'm not exaggerating. So, for a large telescope at least, not for Raphael's backyard telescope, but for a large telescope, the light would be spread out over a large area. And then, I mean, it makes no sense really, but of course you could compute the strain ratio also for here, but just say, so how much brighter is this than this? And then you typically end up with 1% or less. So that's why if you have a large telescope and you want to see a faint star, and you get close to the diffraction limits, you turn on adaptive optics, the brightness here in this area will dramatically increase, and immediately you get 50, 100 times brighter sources in narrower sources. This is what makes it so important to get to the diffraction. Okay, so there are two reasons for large telescopes. As we've been discussing, the angular resolution and the light gathering power. So that's something we discussed last time, signal to And we should say one more word about this factor, because under nominal conditions, the signal to noise of a point source depends on two parameters, namely the integration time and the telescope diameter. We know that the signal to noise from last time, and that has to do with the Poissonian statistics. The signal to noise is proportional to the square root of the integration time. Right? We already said on Tuesday, if you integrate, well, if you want to get twice the signal to noise, you have to integrate 4 times as long. But it also, if you have a larger telescope, then because you have more light gathering power, let's say, then your signal to noise also increases with the square root of the telescope. And then you can put the two factors together. I put this minus in the exponent in parentheses, because if you simply mathematically combine the two, you get a plus here, and that is just the opposite. This requires more explanation. But don't worry about the sign here. The point is that the integration time is proportional, essentially, to the inverse of the telescope diameter to the 4th power. If you have a point source and if you're at the diffraction limit, if you get rid of the signal. So that means that if you have a 40-meter telescope, you can see sources within 1 hour for which you would have to integrate for 700 years with a 1-meter telescope. And this is a very important result, because that explains why people are dreaming about large telescopes.
Size matters.
Size matters, indeed. Now, of course, the fact that, as I said before, it's only for point sources and you need to be diffraction limited. Right? The technical challenges to get to the diffraction limit, no aberrations, no atmospheric turbulence, whatever, with a 40-meter telescope on the ground are substantial. This is very tricky. But 700 years, I mean, there is no way you can ever, with a 1-meter telescope, do something, 1 hour. 1 hour. Nothing.
I was wondering if it's possible to think that the signal to noise ratio of a very large telescope also scales as the 3-parameter square, or what? I just trying to see if I can use this.
Yes, but then if it scales with the C, indeed. But of course here we have assumed there is no C. Right? This is only true if there is no C. If there were C, so if the angular resolution would not follow that law, but would be fixed, say, to 1 arcsecond because of the C, then this term would completely go away and you would only have this dependency. Right? So that would make a huge difference. So that's why people are always trying to get rid of the C, especially for large telescopes. Okay, so I've been spending way too much time so far. Let's talk about telescopes briefly. Of course, I have to refer to the Dutch lens maker Hans Lipperheij, who a bit more than 400 years ago, he applied for a patent for so-called spine lenses. So he had some idea for putting lenses together to see very far. He was not an astronomer. He did not think about astronomy. He just went to the capital back then and said, "Here, I have an idea." And they immediately said, "Don't tell anyone, because you can use it to spy ships, right? It will give the Dutch an advantage because they see the approaching armada much sooner than the others, if you could look that far." So he was given a lot of money and sent away not to tell anyone. But Galileo heard it anyway, half a year later. So that's about the time it took news to travel in Europe at that time. So half a year to get across the Alps. And Galileo was then the first time to apply this to astronomy, looking at primarily solar system. Newton then, this was all based on the lenses, essentially from Lippershey, Newton, of course he made some improvements. Newton then built the first reflector. So reflector means, of course, mirrors that reflect the light rather than refractors, lenses refract the light. And Kepler has then further improved the reflector, and then you can see the early telescope. So this is a 4-foot refractor, right, that size. And of course, there were no concrete buildings with computer-controlled electron motors. So this was all, the telescope, the tube here was all put into some structure made of wood. You had to turn it around in order to track the source of the sky. So this is, well, obviously there is some limit you can put just on a tree, essentially. So that at the time, of course, these were the biggest possible telescopes. You had to be able to move it, and well, obviously when it rains, then maybe the wood expands, and this was challenging. So nowadays there are more sophisticated, stable things. You always have a dome around the telescope, but there are two general types of telescope mounts. One is an equatorial mount, one is the azimuthal mount. I think you probably heard this before. The advantage of the equatorial mount is, well, you probably in Ecuador you don't care. But in any other latitude, you need to make sure that this is how this is oriented really, and so you can't move one of these telescope mounts to any other place in the hemisphere. And so the advantage of that is that if this is oriented along the polar axis, when you track the source on the sky, you only have to turn it around the declination axis. And when you observe, at least in the old days when you were there and had a finder scope and you were trying to make sure that it's not, that you really track it exactly because you were continuously integrating on your photographic plane, this was very important. So it follows the Earth rotation, it's easy to operate, but it's large. I mean, this is a picture of the Yerkes Observatory, which is the largest existing refractor. It has a big lens of about 1 meter in there. And the interesting thing here is actually, it's very impressive. It's a beautiful observatory. If you ever have a chance to visit the US, try to make a trip to Wisconsin and see the observatory. It's all wooden floors. And the thing is, I mean, you can see it's big. So the human being is like that. And when you track something on the sky, because the telescope here rotates around that axis, then the whole telescope, the observing floor, moves up and down. Because otherwise, the observer is sitting here. I mean, how the telescope, of course, takes a different angle, and then this guy would have to jump in order to go through. So the telescope floor is here on huge steel cables. Then some motors lift the floor up and down within the dome. Very interesting. But you can see, I mean, by nowadays standards, the volume that you need for this telescope is a bit overkill for the size of the telescope, the pupil. You have a 1 meter pupil, and the telescope, the dome almost as big as whatever, some cathedral. So the more compact solution is to have simply an axis that is horizontal and one that is vertical. But then, of course, when you move something, it does not follow the object on the sky. So the control is much more tricky, and usually you need a computer to do that for you. Okay, now we'll just apply what we heard before to the telescope optics, because I think this is very important. If you have a spherical mirror, and it's like the same picture as we had drawn before for the spherical lenses, but now for a spherical telescope mirror, you have spherical aberration simply because the light from outer parts of the pupil have a focal plane, or focus on a plane, that is different from the one that is closer to the optical axis. So the good thing about this is that because this is symmetric, there is no preferred orientation. So this picture here would look exactly the same if I were to look not at the star that is here, but if I were to look at the star here, it would be the same. Because this is just a sphere. So that it doesn't matter. There is no preferred axis. If I use a parabolic mirror, I can get rid of the spherical aberration. I can get rid of it. Let's just look at the blue lines here. We said before, for the spherical mirror, the focal point of that ray would be maybe here, and of that ray would be here, and of that would be over here. The parabolic mirror takes care of that. So all the light from the points above the pupil will be focused in the same focal point. That's great. The problem is that if you look at the star or a source that is not on axis, but slightly offset, like indicated here with the green rays, they have a different focal point. So now we have transformed one problem into another. Now we have all the rays from the whole pupil coming to the same focus, but if we say we look at the star cluster, then you have the stars in the center maybe focused, but you have the stars at the edges of your image focused to a different point, and that means that they're fuzzy, they're not sharp in the image. And this gets worse the larger and larger the mirror is. This is essentially the difference between the parabola and the sphere determines the shape. You could overplot in your mind, you could overplot the spherical shape here. And so for larger telescopes, this becomes very significant, and this also determines the field of view of the telescopes. So bigger telescopes usually have small field of view. And some people are shocked, but with, say, and one of the big telescopes we're referring to, you would have a hard time to image the full moon, for example, because the field of view is smaller than the angular size of the full moon. There are, however, telescopes that there are two types of telescopes that should be mentioned in this context. One is the Schmidt telescope, which is still a very popular telescope for surveys. And as I mentioned before, the problem with the spherical mirrors is that rays at different distance from the optical axis have a different focal point. But then Schmidt, I think it was a Polish astronomer, he added a correcting plate, like an odd-shaped lens here, that took care of these aberrations, that essentially added some optical thickness here in the center. So the plate is essentially just thicker here and thinner here, and that compensates for the difference. And so you can get all the rays focused at the same plane. So this is a great idea to provide telescopes with a large field of view, 5 degrees of view or larger. However, there's a problem in the sense that above your telescope you have to add this plate. And so since this is a glass plate, you can use some kind of glass and you polish it that it has exactly that shape here. But of course, it's hard to make any polished glass plates that are larger than a meter. It's easy to break any kind of glass, you probably know from home. But if you then have a thin glass sheet of that size, it's really tricky. And then if you look, actually if you look at the big telescopes nowadays, whether it's the DLT, NTT, Keck, William Herschel telescope, whatever, larger telescope, any telescope of 3, 4, 5, 8 meters, they usually are not simple parabolas, but are actually a combination of 2 hyperbolic mirrors. So, and hyperbolic, parabolic shape is pretty easy. Hyperbolic shape is given by this equation here. And the advantage is that they eliminate some of the aberrations that are given by the simple aspheric parabolic mirror. And this was in first investigated by two astronomers, Ritchie and Gutierrez. And nowadays, as I said, most of the telescope are actually in this configuration, combining two hyperbolic mirrors. Well, obviously the primary mirror and the secondary mirror there, they have this shape. And this is the concept for most professional telescopes nowadays. So you have two mirrors. They're not too far from parabolic. So much, if you have a smaller, for many observatories in this world, you always find a separate telescope for survey functions. And those were always the Schmidt telescopes, and these are the typical professional telescopes. Okay? And then when I said field of view, let me just say what I meant, the usable field of view, which is limited by all these aberrations, field curvature, coma, stigmatism. At some point, of course, you also start vignetting when you look at larger angles. For some, I've just listed it here, for some telescopes, for a typical famous Schmidt telescope, or the 5-meter Hale telescope, so that's the Palomar telescope in California. That's the new technology telescope of ESO on La Sierra in Chile. And what is expected for a 40-meter DLT of different type, RC stands for Ritchie. So the real field of view that people can use is only a few arc minutes, essentially. Even goes down to something like 10 arc minutes or even 5 for an even larger telescope. But for large or existing large telescopes, it's more like half a degree. Okay? And again, this is about the size of the boom. So the message to take away is that big telescopes have small field of view. You need to know exactly where you're looking. They're not going to explore the whole universe. If there are big telescopes, they're not very suitable for large sky surveys. They need to have some information from other observations to know where to look, essentially. And I'd like to finish with that, because then we know where to put the instruments. Because so far we only have 2 mirrors. And at some point, of course, we want to add some instruments to the telescope. And we need to get the light from the sky through the telescope to the instruments. And this is illustrated here for, of course, a reflecting telescope or a refractor. So it's essentially the same. And the difference between a Cassegrain or a Gregory telescope or a Gregorian telescope is where you put the secondary mirror. I mean, you can imagine that you would automatically get a focus here from the primary mirror. And here is the focal plane, and if you put the secondary mirror before that, then this is a classical Cassegrain configuration. For the Gregorian mirror would be here behind the focal plane. So you have an intermediate focus here, which is nice. You can put some test mirror in there. But it's bad because it increases the size. Right? Remember, I think normally the telescope looks up. So you have to build a dome around. And the smaller you can make the distance, the smaller your building, the cheaper the telescope. So you put this, so you have essentially 4 different typical types of foci. Finish with the next slide, I think. So of course you could say, I'll take out all the secondary mirror altogether and I just use the primary focus. So this is probably some of the images where you see Edwin Hubble sitting in the prime focus, because there you have the largest field of view, and you can put a big photographic plate there. That's what was done a long time ago, at least. And then that was a real adventure observing at that time. You had to sit there all night. It was cold, like around the freezing point. You could not move. You could not take liters of hot coffee with you because you were not supposed to leave that cage during the night. And so this was real challenging. This was the part where you really needed students. to do all the observations and work hard, and then you feed the light through the hole in the primary here to the bottom. But there are other ways. You could add a third mirror. You could add the third mirror here somewhere and feed the light out. And then you put the instrument there. And the reason why this is useful is because at this point you mount the instrument to the telescope. This is great because you will always look up in the same direction. But the problem is, as the telescope moves, your instrument also spins around. And if you have a very delicate optics there, that means it will bend and flex, and then it will not be very stable. In this case, you can put a big instrument here. And as we know, instruments are becoming bigger and bigger, weighing tons. Really thousands of kilograms. That's the weight for modern instruments here. And then it's much easier to put this on a solid, heavy instruments on a solid platform. The problem is that with this configuration, and this is something you can work out yourself, as the telescope moves, the image will rotate on your detector. So you somehow have to compensate for that, because this breaks essentially the symmetry. In the Cassegrain configuration, you don't break the symmetry. It's always one axis in the same way, but in this case, as the telescope moves, the field starts rotating, and then you have to rotate the whole instrument there as well. And if you look at observatories, old observatories at least, you often find a Kuderum that looks like the dungeons somewhere in the basement. It looks like they were torturing astronomers there. So it's all dark and huge and lots of dust and spider webs nowadays. But this was done to put high resolution spectrographs there. And now remember what we said about slow or fast beams. In order to get the beam down there and not have 5 foci in between, so right, you feed the beam over many mirrors, so you really need this slow beam where it's converging very slowly in order to get all the light here down to the beam. And then you can put that, because it's in the basement, you have space, you have a large available platform, and then you can put high resolution spectrograph there, which requires a lot of optics and space. This is what you can find in most old observatories. And yes, and this is about the instruments, and the rest comes next. Okay, any questions? Yes, please.
Phrase, some features, short